Now, one technology that's really invaluable when we're talking about surveying and understanding geography and things is GPS. Now, GPS, as it's known now as Global Positioning System, should really be referred to as the GNSS, the Global Navigation Satellite System, because GPS is just one form of a GNSS, which is the Navstar GPS American system. But there are a number of different systems in different places around the world, like Galileo, the European system, GLONASS, the Russian system, and other ones, some of them by regional areas like in India and Japan, for example. These will typically comprise of a receiver that will be able to receive information from various satellites. A lot of receivers these days will do multi-satellite systems, so they might be able to receive data from Navstar, GLONASS, and Galileo, for example. And based on that, they'll be able to combine it with mapping data or GIS systems to plot our location on a map, for example. Or at the very least, give us our ESEF and we convert to latitude and longitude and altitude data that we can use for all sorts of applications. Now, GPS receivers come in many different shapes and sizes. Over on the left was the very first GPS receiver I owned, which was a Magellan 315. That GPS receiver would be over 20 years old now and doesn't have near the accuracy nor the capabilities of some of our modern GPS receivers. Above we see a mobile phone, and mobile phones have GPS with our satellite navigation and things inbuilt that overlay that GPS data over mapping, allowing us to plot routes and know where we're heading and know things like speed of travel that we're going on as well. In the middle, we have a military GPS system, which uses encrypted GPS, which gives us high accuracy, but also stops us from being spoofed. We also have a civil GPS receiver there that we can use in the field for high accuracy GPS. But GPS receivers have really come down in size, and you see this one just above me. These are the size of, well, just over a 50-cent coin. They're quite small, can be run on batteries and connect to a little microcontroller. Some people use these for tracking vehicles and things like that, looking at where they're going, for example. GPS has many different applications and it's used for lots of different areas. And the sort of GPS receiver we use will vary depending on what sort of application we're dealing with. So then how does GPS actually work? Well, essentially we need 4 satellites or signals from 4 different satellites. The 3 satellites will give us our position, and the 4th satellite will correct for errors in our receiver clock to give us a much more accurate position. Now, the GPS satellites broadcast 2 things. They essentially broadcast the map of where all the GPS satellites are. So the GPS receiver knows where all the satellites are and can use that for its calculations. And it also computes the time that the message was sent by the GPS satellite. Based on that, it can compute our ESEF data for our location and hence the latitude, longitude, and altitude that we typically normally see as our GPS data that we use all the time in conjunction with maps and things like that. Now, at various times, we've got different number of satellites within our constellations. Navstar's got approximately 32. And those satellites have a highly accurate atomic clock on board to allow them to do highly accurate timing. They do have several sources of error. For example, atmospheric conditions that those signals actually need to pass through, which will change over time and change as the atmosphere changes. Multipath, where signals can bounce off objects, for example, a hillside or within a city, and also clock synchronization. Now, our GPS receivers will take all these different signals from our GPS satellites, compute our position, and work out what our latitude and longitude and altitude and some other things like our speed, for example. And then they'll put that information out, typically as a GPS string. There's a number of different GPS strings like the RMC string, the GGA string, the GLL string. Each of these strings have different data depending on whether we're interested in latitude and longitudes, whether we're interested most in altitude, whether we're interested in bearing or speed. There's a number of different pieces of data out there. Now, they consist of a series of numbers and letters that we can actually just read. And here's, for example, is our RMC string, which contains our latitude, our longitude, our speed. It tells us what our date is at any point in time. It has a checksum there. It tells us our magnetic variation. And it also tells us whether we've got a good string or a bad string. GPS has a number of problems though, with accuracy, with jamming and blocking, but also with spoofing as well. So in terms of accuracy, GPS is actually quite accurate these days. A few decades ago, something called selective availability was used, which significantly reduced the accuracy of GPS for civilian users. Once that was turned off, the accuracy of GPS significantly improved to allow us to have our satellite navigation systems, which are quite accurate these days. Now, GPS should have within the standard an accuracy of at least 7.8 meters with 95% confidence. Realistically, and particularly on the ground, it's typically a lot better than this. And the reason it's a lot better on the ground or in that particular plane is our GPS accuracy in terms of latitude and longitude is significantly better than our GPS accuracy in terms of altitude. And so this standard GPS with an accuracy of maybe 3 meters in the one plane is fairly good for course navigation between some waypoints and things, but it's not accurate enough to go through maybe a doorway or something with a robot, or having a car that's just driving itself entirely on this. Now, one thing military GPS does, besides encryption to prevent spoofing and things, is to transmit on 2 different frequencies. With these 2 different frequencies, we can do corrections based on atmospheric conditions, changes in the ionosphere, which can significantly improve accuracy. Talked about multipath, and maybe sometimes you've been in a city with high buildings and things like that, and you notice your GPS accuracy is significantly worse than what it normally is. And it's because those signals that you're not getting direct line of sight of, they're bouncing off various objects. Likewise, if you're trying to use GPS indoors, we get something where a lot of our signals have been blocked. These GPS signals are pretty weak, really. And so they can be jammed by transmitter that's transmitting over them and basically jumbling up any data they would be receiving from the satellites. In 2007, this happened, although accidentally in California, when a Navy ship was transmitting at this particular frequency and jammed a whole lot of GPS signals. A whole lot of things went haywire. ATM systems, where people were trying to get their money out, they use GPS for synchronization because they've got really accurate synchronization between GPS systems. So they went offline. Obviously, car satellite navigation systems and things weren't working accurately. Air traffic control wasn't working accurately. A whole lot of areas were not working accurately because these rely on GPS as a backbone. Now, although jamming's possible and you can buy devices to do this, which are very illegal and you shouldn't do it, you should not use GPS jamming. GPS blocking is something that is more common. And GPS blocking, we're basically not receiving that signal, not because that signal's been jammed by a different signal, but because we just can't receive it anymore because they are quite weak. Sometimes our GPS signals are blocked if we go inside or in an underground car park or in a cave or something like that. We're just not getting those signals anymore. We don't get them underwater either. And we don't get them when we're walking in a dense forest or something. They don't penetrate through the trees very well. And if we've got lots of adjoining buildings, for example, those signals might be bounced off multiple buildings. And so our time of arrival will be a bit different as well because of these indirect reflections. One other thing that can be done is GPS spoofing. So before, with GPS jamming, the signals were jammed and basically they were ridden over. With GPS spoofing, we basically create a pretend satellite. And that pretend satellite, we can feed the GPS system data, and it believes that data is coming from a real satellite, but it's coming from a pretend satellite. There's a story down there that you can look up from Wired in 2012, where someone took control of a drone by spoofing the GPS signals for it with a local transmitter. And the drone thought it was flying along some GPS waypoints. And those GPS waypoints are all well and good, but the GPS didn't realize it was at the wrong position. It thought it was somewhere else because the signals that were sent from the satellite had been spoofed. Now, that drone wasn't a military drone because military drones use military GPS, and military GPS can't be spoofed. Now, there are some other anti-spoofing mechanisms besides having a military-style encrypted GPS signal. One of them is using our IMU data, so accelerometers and gyroscopes and things inside a mobile phone, for example, to work out using inertial means where we're traveling or where we are and comparing that with our GPS and to work out whether we're being spoofed. Likewise, we can use data from assisted GPS mechanisms, like looking at Wi-Fi hotspots and maps of where those Wi-Fi hotspots are to work out whether we're expecting it to be. Just like when we look out a window and see a sign, welcome to Victoria, but our GPS tells us we're in WA, well, we're being spoofed somewhere along the line, whether someone's putting up fake signs or whether our GPS is being spoofed and telling us we're in a different location than what we actually are.